Dear friends, this is my
So
third and last
concept with
lecture. Where from the very first lecture, as I told you, I will be talking about with regard to materials and especially with regard to the advanced materials. Where in the first lecture I discussed with regard to crystals, the quasi-crystals, the nanocrystals or quantum dots. In my second lecture, I talked about ceramics. Now, this is the third and last lecture where I will be discussing certain concepts with regard to materials. And if you have any doubt, you can email me out also. You can reach out to me also, right? So, what are the concepts which I would like to share with you? Of course, many of the persons or many of the teachers may be working in this field, but I want to share my knowledge with you. So I will be talking with regard to the concept of a multi-ferrite material. Okay. Then after finishing this multiferricity, what is multiferrite and what are the multiferrite materials, I will be talking about EMR materials, which is closal magneto-resistance. And in the third and the last, if the time permits, I will quickly go through the superconductivity phenomena. Superconductivity, which is also very important in the material science field. To begin with, let me tell you that as far as multiferrite or CMR materials, or for that matter, ceramics, for that matter, the superconducting materials, they are all complex materials which are used for the new technology. So accordingly, what I have said here that the discovery and development of the novel complex material with interesting and potentially useful properties is crucial for our scientific progress. As I told you that certain recent Nobel Prizes on conducting polymers, high temperature superconductors, which I will be talking about, quasi-crystals, quantum dots, have resulted from the synthesis and the development of the materials with exciting properties. So these discoveries are often driven firstly purely by scientific interest and later on its technological benefits were realized. So, at the forefront of these materials are today involves materials with tremendous properties with regard to electronic, transport, magnetic, superconducting properties, which today I will be talking about. So, all these materials, which are basically the advanced materials, the new technology materials, they are all categorized under the quantum material, which display anomalous forms of superconductivity at elevated temperature and novel form of magnetism that responds strongly to an array of perturbations. So, progress and development in synthesis technique is important to develop higher quality material that expose novel electronic material. So let me come to the first part of my research, first part of my talk, which is multiferrite, or what you call it as magnetoelectrics. Well, as far as multiferrite is concerned, or for magnetic material is concerned, if you remember, yesterday I was talking about ferroelectric properties of a material. And where we have the field description of E versus E. E stands for polarization, E stands for the electrical field. For materials which shows the magnetic properties, ferromagnetic properties, you have BH curve, or in that sense MH curve, which is, we call it as a hysteresis zone. And another field description is stress sigma versus epsilon, the strain which is developed in certain materials. So you know that initially during 1950s, the concept of magnetoelectrics, as all of you know, that experimental evidence was given 1960s, and there is a recent resurgence in the interest as far as their experimental and theoretical is concerned, and that recent resurgence of the interest is in the field of multi-ferrite materials. So what actually is multiferrite materials, right? So remember one point. Let me tell you one thing. Yesterday I talked about ferroelectric materials. Okay. With ferroelectric, let me say that ferroelectric materials actually are concerned with the charge domain, positive and negative charge. Fair enough. Ferromagnetic domains are concerned with the magnetic dipoles like North Pole and South Pole, that is Fe2O3 iron oxide. So multiferrite materials are those materials which are the combination of magnetic dipoles and the charge dipoles. So it is very essential to understand that the coexistence of magnetic dipole and the charge dipole is very, very difficult. And when it is coexistence of, is there any problem? There is mic open for some participants. Please.
Hey,
Okay.
खाल्लं
So
झोपलं ना
there is a
सांगच का
difference. Please, I'm
म्हणजे
getting
पैसे
disturbed.
पैसे
Please
उतरू येतं एक
unmute your
मस्त
mic.
पैसे
Mute your mic. Okay. Am I audible for others?
कर कर पैसे पाडायचे प्रश्न
Am I
तू उतरून
audible?
काढ
Please
उचलणार
respond.
पाठ कर विचारणार
Hello?
पाठ कर
Yes, sir. Okay.
Yes, sir, you are audible.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So, the primary concern of a multiferrite material is the combination of two properties
तिथे
in
घेते
a
कोण
same
पण
material,
लिहून काढ कुठे
magnetic
कम्प्युटरचे
properties and the charge
कम्प्युटर होई
properties.
नाही
So that gives rise to
होई
the
घेऊन
multiferrite.
सापेसे सापेसे घे होई कुठ्यामध्ये
So crystals can be defined as multiferrite when
मध्ये कसं
two
गिरी
or
आहे
more of the primary ferrite properties are united in the
मध्ये
same
कसं गिरी आहे
phase. This was discovered by Hans Schempp from Switzerland. So primary ferrite material is basically based on the switchable domain. Definitely excludes the anti-ferrite forms of ordering. That means it includes the ferrite form of it. So that means ferromagnetic systems you have spontaneous
मोबाईल
whereas in ferroelectricity you have
मोरी मोबाईल
spontaneous
सुरू करून इकडे
whereas other type of materials where you have stress strain, you have ferroelasticity, where you have spontaneous strain, and ferrotoridicity, where you have spontaneous magnetic vortices. So, what actually is the idea of a multiferrite material? What actually is the idea of multiferrite material? As I told you, you have three main Aksha, please mute your mic.
ಕಾಲೇಜ್ ಕರೆಕ್ಷನ್ ಮಾಡ್ತಾರೆ ನೋಡ್ರಿ ಮೇಡಮ್ ಕಾಲೇಜ್ ಹೆಸರನ್ನ ಡಿಸ್ಕಲ್ಲಿ ಕಳಿಸಿದ್ರಲ್ಲ
Just a minute.
ಯಾವ್ದು ತಗೊಂಡು ಕೂಡ
Participants,
ಮೆಸೇಜ್ ಹಾಕ್ಬಿಡಿ ಅವ್ರ ನಂಬರ್ ಸೇವ್ ಮಾಡಿದ್ರು ಯೂಸ್ ಹಾಂ ಹಂಗೆ ಕಳಿಸ್ಬಿಡ್ತೀವಿ
mute mic करो भाई.
नाही भेटली
आपने नहीं किया हुआ है. आपका
ಎಲ್ಲ
आप एक चेक करो.
रोज काय चेकच करायचं होमवर्क दिल्यास मग होई केल्यास नाही कम्प्युटरला
Sorry for the disturbance. Please, let me go ahead. So, I was talking about the two different types of
उठ और पटपट
switchable
वेळ नाही
domains, which
ते
is
सगळं तर काय
either
करणार होती
can
सातला
be
पेपर होते
ferromagnetic, ferroelectric, ferroelastic, ferrotoridicity. So, let me talk about idea of magnetoelectric effect. So, when you talk about multiferrite material or magnetoelectric effect, you have three main the system, that is electrical field, magnetic field, and mechanical stress. Associated with it, in a ferroelectric material you have polarization, in a ferromagnetic material you have magnetization, whereas in a ferroelastic material you have mechanical strain, which is epsilon. So so P versus E will give rise to a ferroelectric material, M versus H will give rise to a ferromagnetic material. So this will give rise to a this will give rise to the so actually multifluoride material is combination of either the ferroelectric or ferromagnetic, ferroelectric or ferroelastic, or ferroelastic or ferromagnetic. So combination of any of the two will give rise to the magnetoelectric effect or will give rise to a multifluoride material. So you have if you have the combination of these two, it will be known as magnetoelectric effect. So what actually is the multifluoride material? So you can see again this diagram where you have a ferroelectric material which when it is combined with the ferromagnetic material, and the combination of the two properties will give rise to magnetoelectric effect. The combination of these two will give rise to magnetoelastic effect, and the combination of these two will give rise to piezoelastic effect. So any of these two will form a multiferroid system. So you know that if you talk about a ferrite material which was discovered a century ago in a ferric oxide material, so ferrite materials can be ferroelectric, ferromagnetic, ferroelastic. So if we talk about this, so multiferrites exhibit two or more of these properties simultaneously. The coexistence of ferroelectric and magnetic order is possible simultaneously because of the inversion symmetry is broken and magnetism is present. So you can see that there is a very small group of multiferroid material over here, right? This is electrically polarizable material. This is magnetically polarizable material. These are ferromagnetic. Out of these magnetically polarizable material, a small domain is in a ferromagnetic material. Similarly, out of the electrically polarized material which I was talking about, which includes piezoelectric material, a small domain is a ferroelectric material, because I told you based on the crystallographic direction, based on the non-centrosymmetric inversion properties, and out of these, a ferromagnetism and ferroelectric, there is a small domain which will give rise to a multiferroid material, or in that sense, magnetoelectric material. So, what is basically ferroelectric and ferromagnetic? Most promising for these are materials which is most promising for application, but not many compound exist, because for a ferroelectric to exist, it likes p-d-n orbital with n is equal to 0. Whereas for the magnetic materials, it also likes p-d-n orbital, but your n is not equal to 0. So existing ferroelectric are usually antiferrite with only a weak ferromagnetic or ferroelectric component. So the quest for strong ferroelectric ferromagnetic material at room temperature is still a cause for being solved. We have multiferrite material, but they show the properties at elevated temperature, at higher temperature. Okay. So again, this will show you the hysteresis loop for a ferroelectric material. For a ferromagnetic material, this is Pe, this is Mh. For a ferrotoroidic material, you have Ps, and for ferroelastic, you have epsilon into sigma. And for a ferromagnetic material, you have the external stimuli is magnetic field. For ferroelectric, it is electrical field. For ferroelastic, the strain. For ferrotoridicity, it is the vector, force vector, whereas this is the ordered parameter, polarization, deformation, toroidization, magnetization. And if you talk about inversion, for a ferromagnetic, the inversion symmetry is preserved. For a ferroelectric, it is broken because you need not to have symmetries, because this is non-central symmetric elements. For ferroelastic, it is again preserved, and ferrotoroidic material, it is broken. This is the time reversal concept of these materials. So multiferrite can be of two types, single phase and multi-phase. So these are some of the naturally single phase multiferrite materials. These three natural crystals, they are multiferrite. One is congolite. This is the formula which is based on iron, boron, oxygen, and fluorine. Cubernite, it is manganese feldspar. Chabersite, so this is again, these are the naturally occurring single phase multiferrite composites. Okay, but the most important properties are observed in a composite multiferrite. So what actually is composite multiferrite? Now from here you can understand what basically means of multiferrite. Yesterday, if you remember, I was talking about these materials. So this is now handy for this lecture also, because yesterday I talked about barium titanate, which is a ferroelectric material, which is also a piezoelectric material, or in that sense, lead zirconate titanate or barium lead titanate. This material shows the charged domain. Okay, there is another material, cobalt ferric oxide, or terbium doped dysprosium iron. So this material shows the magnetic properties. If we combine these two materials, then these two materials will be forming a multiferrite composite material having charge properties and the magnetic properties. So magnetoelectric effect is a product of the effect. That means you have to mix in such a ratio that the properties of the charges and the properties of the magnetic domains should remain over here. So you can also see here, you have a particulate where the first layer is a piezoelectric, second is magnetostrictive, that is a magnetic material, and this is a ferroelectric material. Right. So this is the report of a paper which was published in Phillips Research Report during 1970. Their first composite magnetoelectric effect was observed in a material of barium titanate / cobalt ferrite, which I was talking about. So if you see that the magnetoelectrical coupling, this is coupling between the magnetic and electrical effect, which is measured by d by dh of T. It has a value of 130, whereas its coefficient is having a value of 320 Pascal Tesla volt per meter. And if you compare the value of alpha with a single phase multi-composite material, with a single phase multiferrite material, you can see its value is 4.13. TbPiO4 is having a value of 36.7, whereas there is a tremendous change in the value of this alpha, which goes up to 720. So multiferrite composites, that is a composite which is consisting of the ferroelectric properties and the magnetic properties can be combined together. They can also be prepared in a nanocomposite form. So people are working on the nanocomposite. So this is self-assembled nanocomposite multiferrite where ferromagnetic domain and ferroelectric domains are being formed on a substrate of strontium titanate. It is the substrate where these layers are being formed. So you have ferroelectric properties of barium titanate, you have magnetic properties of cobalt iron oxide, and the combination of the two will give rise to a multiferrite composite. So this is one such image of a multiferrite composite prepared in a laboratory. Of course, so this is my result in our laboratory, where I have tried to combine lead titanate, which is a ferroelectric material, with that of an iron, which I have taken as a hexaferrite, strontium hexaferrite. You have seen the reports are showing for orthoferrites, the ferrite, which is simple oxides, but here it is a hexaferrite material where you can clearly distinguish between the magnetic domains and the charge domain. magnetic and the white portions are covering are basically the ferroelectric domain. So after giving this brief of this multi-ferrite composite, let me talk about another important aspect of the materials, which is closer magnetoresistance. So this is also related somewhat with these materials, but now we are not talking about the multiferricity. Multiferrite, remember, it is the combination of ferroelectric or ferromagnetic or ferroelastic. Any of the two combinations will form a multiferrite material. But there are certain materials which will give rise to a tremendous change in the resistance if it is placed in a magnetic field. So that is what is magnetoresistance. So closal magnetoresistance, a change in the electrical resistance of a material responds to a magnetic field. Closal means exceptional or astonishing. However, you have another type of materials which is, you call it as GMR material, giant magnetoresistance. So consider, you all know about magnetoresistance, I need not to talk about this, but what I am talking about is the physics or is the features behind the observation of these materials. What actually is happening inside the material. So in a giant magnetoresistance, in 1988, thinly layered materials were found that increase or decrease their resistivity by 20% or more in relatively weak magnetic field. Hence the word giant, which is called magnetoresistance or GMR. The basic effect depends on the alignment of electron spins at the interface of different kinds of magnetic material. However, during 1993, a material was found that could increase or decrease resistance not by a few percent, not by 20%, but by the orders of magnitude. Hence, the word closal means tremendous, astonishing. So this was again observed in certain materials. Every material cannot be a CMR or GMR material. So this is observed in a magnetic materials which is based on manganese oxide. Remember, discovery of huge magnetoresistive effect in the manganese oxide class of materials has rekindled the intense interest in these systems for different reasons. So the materials which I am talking about here is La, lanthanum, A is either strontium, calcium or barium. You can replace the element A with that of the lanthanum, then MnO3. CMR offers potential in number of technologies which include read or write heads in magnetic recording, media, sensor and spin polarized electronics. CMR material is also interesting from the fundamental point of view. In contrast to the traditional ferromagnetic, which are iron oxide or cobalt or nickel, where the spin system is isolated from the lattice. In the manganite, the charges, the spin, the lattice degree of freedom are all strongly coupled together, leading to the delicate balance of interaction that gives rise to a rich variety of physical phenomena of current interest in the solid state physics or the condensed matter physics. So this is a chart which actually shows you the magnetization, the what you call it as resistivity and magnetoresistivity effect against the temperature. If you can see this curve, this is magnetization, right? Magnetization with respect to temperature at different applied magnetic field. This is resistivity against the temperature. So you can see that the magnetoresistance against the temperature, there is a transition at a particular temperature, and you can also see that the temperature is ranging from low temperature to the high temperature in the sense up to the room temperature. So So there is a tremendous change in the resistivity, there is tremendous change in the magnetization, there is tremendous change in the magnetoresistance values of, you can see it is about percentage. So at a temperature, the amount of change is about 40, 60 and 80% of its original value at the low temperature. So, closal magnetoresistance predominantly discovered in the manganese-based materials, which is again a perovskite-based structure. If you remember, yesterday again I was talking about a barium titanate material, which is a ferroelectric material. That is also a perovskite-based material, where you have ABO3 formula. A stands for one of the elements, B stands for another element, and O is the oxygen to complete it out. Here we are talking about Re, which is rare earth, M is the metal ions, calcium, strontium, barium you can replace, B is manganese, and this becomes the perovskite type structure. So CMR effect arises because of the strong mutual coupling of the following degrees of freedom, which include spin, which include charge, which include lattices. But how it happens? So the important physical features for a CMR manganite materials are again based on the crystallographic structure, their electronic structure, their exchange interaction. As well as crystallographic structure is concerned, you remember again, this is a perovskite type of a structure where A atoms are lying at the corner of a lattice, B atoms are at the center of the lattice, whereas O is being coordinated with on the faces. So this is the crystallography, and it makes, you can see that these materials, which are perovskite material, have tremendous application or have tremendous different characteristics vis-a-vis ferroelectric, vis-a-vis the closal magnetoresistance properties. So these materials are such having a different type of a structure, which makes it very important material. So this large size rare earth trivalent ions and M divalent ions, which are in A side with 12-fold oxygen coordination, smaller manganese ions are at all these sites. So proportion of manganese ion in +3 and +4 can be respectively changed. So as far as understanding, as I told you that the important physical feature of CMR magnetic materials are basically its crystallographic structure, its electronic structure, and its exchange interaction. So as far as their crystallographic structure is concerned, I have shown you this is the characteristics of these manganite. Because of this, they can adjust at different places. They show you such type of properties. And when you talk about the electronic structure, so the electronic structure is based on the d orbital transition methods, and they are of 5 types. You can see that it exists in EG orbital and it exists in P2G orbital. Now, this electronic structure is based on the crystal field theory, and for those, let me just give you a flavor of what actually is E or what actually is referring to G orbital. E actually refers to the doubly degenerate orbitals. That means there are 2 types of orbitals. Okay, in the when you see the energy band theory, I will talk about later. So you can see it is split into 2 orbitals, right? E basically refers to the doubly degenerate orbital. So it consists of 2d orbitals, whereas T means having triply degenerate orbital. What does this degenerate means? Degenerate means having the same energy, and these are derived from the group theory. So T stands for triply degenerate orbitals, and this is the product of these two, Zx, Yz, and Xy. So in EG, you call it as the doubly degenerate orbital, and in T2G you call it as a triply degenerate orbital. And G basically refers to about the orbitals are great. GER. Okay, I will show you this one. So what actually, yes, this is EG and T2G exists only in d orbital. E refers to doubly degenerate orbital. It consists of two d orbitals. T refers to triply degenerate, which I was explaining you. G basically tells about the orbitals are great. That means great is basically a German meaning, which means German word which means even. They have the same symmetry with respect to the inversion center. So this is the triply degenerate orbital. So you have zx direction, you have yz direction, you have xy direction. So it is in the c direction and it is in the xy direction. If you talk about energy band theory, by taking an energy band theory, so you can see that it gets split into the EG, which I told you, it is doubly degenerate orbital. You can see this can be shown by this, which I have shown three-dimensionally. You can see it is two-dimensionally. This is triply degenerate orbital, so you can see that yz, zx, xy, so it can be something like this. So there is a transition, there is a movement of anti signs. Because of this, there is a change, tremendous change in the magnetic properties when it is placed in a, there is tremendous change in the resistance properties when what we call it as it is placed in a magnetic field. The third type of property, third type of physical explanation is based on the exchange interaction. There is magnetic properties of manganites are basically based on the exchange interaction between manganese ions, spin. So when you talk about manganese oxygen manganese interaction, it is controlled by the manganese p orbital and the oxygen's p orbital. So there is a corresponding super exchange interaction which depends upon the orbital configuration. So if there is a change in the or if there is interaction between the metal ion M4 plus with that of the manganese ion, it will lead to the ferromagnetic. If there is an interaction of metal ion with manganese ion 3 plus and 3 plus, it will lead to ferromagnetic material. So this is the interesting picture where one can understand the CNR properties of these materials. If you talk about ordering, which type of ordering occurs in all these CMR compounds? Most of these oxide materials, perovskite oxide materials, have the three different types of ordering. First is charge ordering, second is orbital ordering, and the third one is the spin ordering. So all these three orderings will lead to the properties of CMR. So what is charge ordering? Simply to make you understand, charge ordering means that there is charge ordering in the manganite is interesting because charge ordering results due to the localization of the charges. Therefore, it is associated with the insulating or antiferromagnetic behavior. There is a double exchange which gives rise to metallicity along with ferromagnetic behavior. Therefore, there is a competition between ferromagnetic material, metallic behavior, and cooperative John-Teller effect, which all are. So now, again, there are certain terminologies which have come over here, which is John-Teller effect. This John-Teller effect is nothing but a spontaneous breaking of symmetry of the molecules in a solid system. When there is a changes going on between these manganese and metal oxide, if you have seen, then there is a breaking of the molecule. That means John-Teller effect is nothing but a geometrical distortion of the molecules and the ions that various electronic configurations. So this is the charge ordering, means charge in because the main magnetic ion in these perovskite material is manganese. Okay, so you have manganese 3 plus, you have manganese 4 plus. So manganese 3 plus is all making the difference. So you can see that in this direction the charges are in the same, whereas while here they are 90 degrees to each other. So that gives rise to the, because when you place it in a magnetic field, they get oriented, they get distortion, but what I was talking about, John Taylor is that. As far as orbital ordering is concerned, the orbital ordering gives rise to the anisotropy of the electron transfer interaction. This can favor or this can disfavor the double exchange interaction or the super exchange interaction in the orbital direction. Hence, it gives the complex spin orbital coupled state, and the orbital ordering is coupled with the John-Taylor distortion. Different types of orbital ordering occurs in manganese oxide perovskite, which is shown like this. Again, you can see that the same when you talk about the crystallographical directions or the field theory direction, your charge ordering is in case of C type. There is 3 different types of orbital ordering: C, F, and A. So you can see the direction of all these orbitals. Another is when I talk about spin ordering, so charge ordering, orbital ordering, and the third one is the spin ordering. So spin ordering is the ordering of the spin of the molecule, the spin of an electron, what you call it as, interaction with the neighboring atoms make the spin of the electrons aligned in a particular fashion. You should remember that for a ferromagnetic material, the spins are all arranged parallel to one another, and this is the type of spin ordering in a perovskite. You can see they are all arranged in a particular direction. They give rise to the ferromagnetic ordering. Whereas you have certain material which is anti-ferromagnetism, so which results when they are anti-parallel to one another. And when we talk about anti-ferromagnetism, there are 3 types. There are 3 types of anti-ferromagnetic ordering. One is A, C, and G type. In the A type ordering, the interplane coupling is ferromagnetic. That means you can see the intraplane coupling, that means these orbital ordering and these orbital ordering, they are in the same place. However, the interplane, this is intraplane, this is interplane, which is other inside of this material. So this is all because of Mn plus, Mn3 plus or Mn4 plus, which are getting ordered. So this is intra, they are in the same direction. Inter, they get opposite. This gives rise to the A type of antiferromagnetic material properties. C type, the intraplane coupling is antiferromagnetic, while interplane coupling is ferromagnetic. So this is the reverse of this one. You can see this is in the same direction, whereas this is in the opposite direction. And totally intra and inter, they are in the opposite direction. So G type is both intra and interplane coupling are antiferromagnetic. So this is a picture which shows that GMR material can be used for various memory devices, which is GMR is a higher sensitivity and better signal to noise ratio, contactless sensor, do not identify mechanical wear. Thin film magnetoresistant heads are produced by the photolithographic processing, which is a prototype of GMR device based on the exchange by spin wall, which has been offered by the IBM for various application points. So you can see that I started with the multiferrite, where ferromagnetism is there, where ferroelectricity is there. Now and then magnetic properties, ferromagnetic there, which is why closure magnetoresistance are there, which type of ordering are there, which type of crystallographic reactions are there. Let me come to the third topic, which is superconductivity. Okay. So when you talk about superconductivity, something like this comes into your mind. Okay. I hope everybody is aware of superconductivity phenomena. No need to explain you, but still, as my talk is about the advances in the material, so that is why I have linked this superconductivity with the advances in the material, vis-a-vis the ceramic material, because ceramic plays a very important role in the superconductivity behavior. Why? I will show you later on. Firstly, let us try to understand what actually is superconductivity. Everybody is aware of the superconductivity phenomena was given by this scientist. His name was Haig Camerlin in 1911. While he was working in his laboratory, he was a Dutch physicist. He was working in his laboratory and finding out the resistance of mercury at lower temperature. He was basically cooling the mercury and trying to find out the resistance. So you know that all these discoveries are just while working or while researching with the various materials, and this one such behavior was observed. So when we talk about superconductivity phenomena, this is really an exciting field of physics. This is a picture which shows the radiation. I will explain it later on. Later on again there is an image for this. Let me first of all concentrate first with the introduction part of the superconductivity, which is the main definition of superconductivity is that the flow of electrical current without resistance in certain metals, alloys, and ceramics. So comes here another the thing which I was talking about. Ceramics at temperature near absolute zero, and in some cases at temperature hundreds of degrees above the absolute zero. Okay, this was the definition. To have a view of the comparison of temperature, I am showing here the temperature in Fahrenheit, in degree centigrade, in Kelvin, because what I will be talking about is superconductivity at low temperature. So water boils in 100 degrees centigrade, so this is in Fahrenheit, in Kelvin. This is body temperature, room temperature, freezing water, mercury freezes, dry ice, liquid oxygen, liquid nitrogen, liquid helium, and absolute zero, which is minus 273.2 degrees centigrade. So an element or intermetallic alloy or a compound that will conduct electricity without resistance below a certain temperature is called a superconductor, and the phenomena is called superconductivity. As we know, resistance is undesirable because it produces losses in the energy flowing through the material. So material becomes superconductor below a critical temperature. This is the critical temperature. The temperature dependent change between superconducting and normal conduction is abrupt. So this is a material. Okay, I will show you in the next slide. This is the person who discovered, as I already showed you the image, the Haig Camerlin, who discovered this superconductivity in 1911. While working with the mercury at very, very low temperature, it was actually looking for the resistance of the mercury at low temperature. Okay. So, as per the theories existing during that period of time, like Lord Kelvin theory, as per the Kelvin theory, he thought that with the decrease in the temperature, the resistance should fall, but at a particular temperature it should increase. However, Matheson theory has predicted that the resistance at low temperature should fall and almost gets the fall should be very smooth and becomes very less at lower temperature. However, in 1904, Dalzier gave a theory that when you decrease the temperature, the fall should be there and it should be zero. But the result he observed in his laboratory was something different. For mercury, when he was working with the mercury, he found that the resistance is slowly and slowly decreasing, and there is abrupt fall at a particular temperature. And for mercury, it was 4.12 Kelvin. For thallium, he then worked on other elements. For thallium again, there was a decrease in the abrupt decrease in the resistance at a particular temperature. It was somewhere greater than 2 Kelvin. For lead, it is greater than 6 or greater than 7. So all has a particular transition temperature. The temperature at which there is zero resistance. That means the resistance, that is the electrons which are flowing, they are not being offered any opposition for the flow of the current. Okay. So the superconductivity was discovered by Camarelli-Lingones during 1911 during the first low temperature measurement for liquid conductivity. While measuring the resistivity of pure mercury, he noticed that the electrical resistance dropped to zero at 4.2. So this was predicted earlier that how should the resistance vary. But it should be like this. But he found out that the resistance falls. And in 1912, he found that this resistance state is restored. That means, the superconductivity gets destroyed if you apply electromagnetic field or high transport current applied. Then at that condition, your superconductivity vanishes out. And in 1900, he discovered this phenomena, whereas in 1913 he was awarded the Nobel Prize for the discovery of superconductivity. So the superconductivity has two outstanding features. One is zero electrical resistivity. This means that the electrical current in a superconductor ring continues indefinitely until a force is applied to oppose the current. The magnetic field inside the bulk sample is zero, which is what we call it as the Meissner effect. Those who understood the superconductivity, they must be knowing that there is a Meissner effect, which is associated with the superconductivity, and there are other associated effects associated with the superconductivity, which I will tell you in the later course of my lecture. So when a magnetic field is applied, current flows in the outer skin of the material leading to the induced magnetic field that exactly opposes the light. The material is strongly diamagnetic in nature. In the Meissner effect experiment, a magnet flows above the surface of the superconductor. So most material will only superconduct at very low temperature, where actually zero. Above critical temperature, the material may have conventional metallic properties, metallic conductivity, or they can be an insulator. As temperature drops below the critical point, resistivity rapidly drops to zero and current can flow freely without any resistance. That is very important part of it. So this is the periodic table where it shows that the elements with the blue, they are superconducting elements. They can be superconductor at a particular temperature but at ambient pressure. However, these green and the periodic table, they are superconducting but at high pressure. They are superconducting, you have to supply high pressure. So the relation for linear reduction of resistivity as temperature decreases is given by this equation. So you can see that the resistivity is very, very small, of the order of 10 to the power minus 23 for a superconductor. Whereas for a non-superconductor, the resistivity is of the order of 10 to the power minus 3. So what actually is the definition before 1987, why this 1987 the barrier, that I will explain later. The phenomena exhibited by certain metals and alloys of continuously conducting electrical current without resistance when cooled to temperature near absolute zero. But the definition now which is given for superconductivity is an electronic state of a matter characterized by zero resistance, perfect diamagnetic, and long-range quantum mechanical ordering. So you should remember whether it is a multiferrite material or a CMR material, I try to explain it what is the behavior, how the magnetoresistance changes. So similarly, let me tell you that whatever the experimental evidences are there, but those experimental evidences are being explained on the basis of the theory. What actually is happening in a material? What is happening? So in 1911, the superconductivity phenomena was discovered. Then there were many theories which were floated to explain the phenomena of superconductivity. But no theory was definite in explaining the phenomena of superconductivity until these three persons, Barden, Cooper, Schreiber, gave their BCS theory, the famous BCS theory, where it says that actually it is a pair of electrons, we call it as a Cooper pair. Okay. The understanding of superconductivity was advanced during 1957. So you can see between 1911, let me tell you also one thing, between 1911 to 1950s or 57, people were various researchers or various research laboratories were after this superconductivity. They were trying to increase the transition temperature. As you have seen that for the very first material, the mercury was observed at the superconductivity was observed in the mercury at 4.1 Kelvin. Then they try to find the superconductivity for other metals, and then they make an intermetallic alloy. They try to increase the transition temperature. So the people succeeded in increasing the transition temperature. At the same time, people were also trying to explain the behavior of superconductivity on the basis of what actually is happening inside the material. So meanwhile, the magnetic effect of the superconductivity was observed, which I told you that superconductivity gets destroyed when you apply magnetic field. The Meissner effect was observed, where you have the magnetic radiation phenomena. But in 1957, these three American physics explained the behavior of superconductivity, which till now is applicable for all these materials. The BCS theory explains superconductivity at temperature. Cooper realized that atomic lattice vibration were directly responsible for unifying the entire system. They forced the electrons to pair up into beams that could pass all the obstacles which caused resistance in the conductor. And they also said this will specifically happen at low temperature. One should remember that at low temperature, what actually is happening, there are a pair of electrons, we call it a super pair. They get stacked together because of that virtual phonon. Because lattice is vibrating, quantized lattice vibration is what we call it as a phonon. So virtual phonon, because of that virtual phonon, those super pairs get entangled and they move in the lattice without any resistance. Mind it. Okay. Further, what is the science? This is the science. The BCS theory successfully shows that the electrons can be attracted to one another. Okay, mind it. We are talking about here electrons can be attracted. So when there are two electrons, because of the force of attraction or repulsion, they should repel each other. However, at this very low temperature, they are attracted to each other. And that attraction is because of the interaction, which is what we call it as a lattice vibrational interaction, which we call it as a phonon. That occurs despite the fact that the electrons have the same charge. When the atoms of the lattice oscillate as positive and negative regions, the electron pair is alternatively pulled together and pushed apart without a collision. The electron pairing is favorable because it has the effect of putting the material into lower energy state. When electrons are linked together in pair, they move through the superconductor in an ordered fashion. One can imagine a metal as a lattice positive ion which can move as if attached by the stiff springs. Single electron moves through the lattice constitute an electrical current. So that single electron will get opposition for the flow, but normally the electrons repel each other and are scattered by the lattice, creating resistance. So what actually is happening over here is second electron passing by is attracted towards this positive region, and in a superconductor it follows the first electron and they travel bound together in the lattice. So these two electrons which team up is what we call it as a super pair. In accordance with the theory, BCS or other, despite the fact that both have the negative charges and normally repel each other. Below the superconducting transition temperature, paired electron form a condensed, a macroscopically occupied single quantum state which flows without the resistance. So, conventional superconductor can be, this is again, Barden, Cooper and Schaeffer got the Nobel Prize during 1972 after their discovery in 1957 explaining this phenomena. You can see that this is some type of animation which I am showing over here. Superconductor versus normal metal. You can see that positively charged atom, electron, this is a positively charged atom, electron passes through causing an inverse distortion. Okay. As the negatively charged electron passes between the metal's positively charged atom in the lattice, the atoms are attracted inward. This distortion of the lattice creates a region of enhanced positive charge, which we call it as distortion, which attracts another electron to the area. And this is something like that. Electron, another electron in the area. So this is area of distortion, right? This is the normal state where when electrons are moving, they get opposed, but this is the superconducting state. When these two electrons move, they get no opposition for the flow. So this is the animation there. Can you see this? A Cooper pair is moving without any resistance. So this is what we call it as the distortion of the lattice, and with the help of the phonons, they move within the lattice, what we call it as a Cooper. Next is Meissner effect, which is based on the magnetic levitation. So when a material makes a transition from normal to the superconducting state, it actively excludes the magnetic field from its interior. This is what we call it as Meissner effect. This is the image of a non-superconductor. When magnetic lines of forces, if this material is placed in a magnetic field, the magnetic lines of forces are passing through the inside the material. But when it becomes a superconducting state, the magnetic lines of forces are passing out of this. They will get become perfect diamagnetic material. This gives rise to a very, very important property in a superconducting materials, which is called magnetic leviation. How magnetic leviation works? Magnetic leviation, what is basically a magnetic leviation? In magnetic leviation, what you did, you place a small magnet in the superconducting state. In a material which is a superconducting disk, you have to place the superconducting disk in a low temperature. That means you have to involve liquid nitrogen. So if a small magnet is brought near a superconductor, it will be repelled because of the induced supercurrent which produce mirror images of each pole. If a small permanent magnet is placed above a superconductor, it can be leviated by this repulsive force. So this lattice diagram means it will be in the floating position. You can say it will not settle down, and you can see this is the magnetic levitation, another image of magnetic levitation, and this is the video which shows that this is the superconducting ring. And if you see the fumes emitting from here, you have placed the liquid, this superconducting disc is placed in a liquid nitrogen so that this material should behave as a superconductor. If you place a magnet on it, then it will start floating. So you can see that this magnetic levitation, if you know, is the basic for the fundamental principle or basic principle for these bullet trains, or what we call it as, which I will talk about the application later on. If you talk about superconductors, so I am exceeding my time. So okay, please remind it. I will take 15 minutes more, right? So if we talk about superconductors, there are two basic types of superconductor: type 1 superconductor and type 2. Let me go quickly through this. This is not that much of interesting because what I want to show over here, this is this. After Meissner effect, another important effect observed in a superconductor is the Josephson effect. Josephson effect, this is the brain Lee Josephson, who discovered that there is a tunneling of supercurrent, that super pairs which tunnel through it. He discovered it during 1960s, and he was given Nobel Prize in Physics in 1973. And remember, he shared his Nobel Prize with two other persons. One was Leo Szilard, who discovered tunneling diode. If you remember, many of the people are who are from electronic background, they must be knowing tunneling diode. So Leo Szilard got for tunneling diode. Then Ivor Gazier was another scientist who got superconducting tunneling effect, normal superconducting tunneling effect, and Josephson tunneling effect is the outcome of the normal superconducting effect. In normal superconducting tunneling effect, what happens is, on this side you have a normal conductor, on the other side you have a superconductor, and these two are separated by a thin film. Okay, so Ivor Gazier first suggested that the electron will tunnel through this thin film and will move towards the superconductor. However, Josephson in 1962 predicted that if on both the sides you place a superconductor, then the Cooper pair will, the two electrons which is in their state, they will overcome the barrier and can move towards other superconductor. So, this is the expression for the tunneling current. Electrical current flows between the two superconducting materials even when they are separated by a non-superconducting or insulator. Electrons tunnel through this non-superconducting region and supercurrent flows. So as I told you, why this is important, because this Josephson tunneling effect gives rise to various superconducting, various important devices which include SQUID, that is superconducting quantum interference devices. The SQUID is very, very important magnetometer where one can detect, and this SQUID is based on this tunneling effect phenomena, superconducting tunneling effect phenomena, and it can detect incredibly small magnetic fields, small enough to measure the magnetic field even in living organisms. This is also important. You can see over here I have given you the values of the magnetic. Our heart is also having certain magnetic field. Our brain is also having certain magnetic field. So this is the value of the magnetic field of our heart, 10 to the power minus 10 Tesla. For the brain, the magnetic field is 10 to the power minus 13 Tesla. Whereas the threshold frequency, the threshold magnetic field for state, that means it can detect the magnetic field of the order of 10 to the power minus 40. Because Because earlier there was vibrational magnetometer which was used to identify the magnetic materials, which was used to give the superconducting materials, but by the phenomena of Josephson tunneling effect, this still was possible. So you have, based on this tunneling effect, you have various instruments in biomagnetism, in scanning speed microscopy, in higher temperature space can be also there. Now, let me quickly finish it out. This is what I was talking about in the superconductivity. In 1986, two researchers, Alex Mueller and George Bagnos, detected the superconductivity. You know that the superconductivity was discovered first in metal, then it was discovered in intermetallic alloys, intermetallic compounds, intermetallic alloys, but nobody was thought of getting superconductivity in a ceramic material. So yesterday also, when I was talking about the importance of ceramic, I have shown you certain materials which will show you the superconductivity property. So this is one such ceramic. So in 1986, they discovered superconductivity in a lanthanum barium copper oxide, where the critical temperature goes to 35 K. So they broke the traditional superconductivity, even if it is very, very low from the normal temperature point of view. And they were subsequently awarded Nobel Prize. One can make these superconductors in the laboratory by, as I told you, by shake and bake method, not to talk about this is a superconducting material which is in the form of pellet. And yesterday I have shown you ceramics which is transparent also. This can be you can say of this type also. You can prepare the superconducting material in the form of a thin film, and the best method is pulse laser deposition technique, where you use a substrate and the laser is then allowed to fall on a substrate, and then the film is produced and you can form the superconducting film. So I will not go into these details. Let us forget about. You are already very late. Yes, this is the milestone in the superconductivity phenomenon. Discovered by Camerling and Onus in 1911, Meissner discovered its effect, which magnetic radiation I was talking about, 1933. In niobium nitride, the superconductivity was discovered, which has a transition temperature of 16 Kelvin. In vanadium, so you can see it started at a 4.12 Kelvin, goes to 17.5 Kelvin. In 62, first commercially based niobium titanium superconducting wire was made. But at that point of time, the researcher was offered a superconductivity research in order to increase the phenomena so that they can remove the losses which is going for the transmission. However, in 1986, superconductivity was discovered in a ceramic material where it goes to 35 K, then 92 K, then 120 K, and in 1993, a compound, a material in the form of ceramic, which has a transition temperature of 133 K. So what actually is the history? This is the history. You can see firstly the mercury, lead, niobium, then intermetallic metals, then alloys, then compounds. Up to 1970s, the situation was something here. The transition temperature, the researchers were not able to increase the transition temperature. However, after discovery of the ceramic by George Bagnos and Mueller, there is a increase in the transition temperature, and at present we are over here and somewhere 193 Kelvin, as I told you in this slide. Yes, 133, but it is above 199 Kelvin as per the latest reports. Okay, this is also so, and very important point over here is that for these materials to find superconductivity, you should have an environment which is liquid period. Very, very expensive material and very difficult to maintain. However, with the advent of these ceramic composition, the liquid nitrogen can be obtained normally and is very cheap. So the tag when in order to get the superconductivity at this low temperature is now overcome, and one can work with the liquid nitrogen because you know its melting point is 77 Kelvin. So you can work with the liquid nitrogen. So that is what the magnetic radiation picture I was showing. I have shown you a superconducting disk in Petri dish where some liquid nitrogen is placed for a brief period of time, and then magnetic is placed, then magnetic starts radiating or superconducting disk. So this is the current situation. If you can see the slide, the lowest recorded ground temperature on Earth. If you see there, I am showing this cursor. This is towards the century of superconductivity. So this I have already shown you. But what I want to say here that this, you know that at various places you have temperature of the order of -40, -50, -60. So this is the lowest recorded ground temperature, and the superconductor is still far off to be tested at the temperature. So today, however, superconductivity is being applied to many diverse areas such as medicine, theoretical, experimental sciences, community transportation. I think I will rush it out here. All I want to show that this is what we call it as the bullet train. The principle of bullet train is based on the magnetic radiation, because when the train is moving on the tracks, it is offered by the resistance. So what is happening over there, that is why you can attain a speed of 400 kilometer per hour. You have the tires where you can throw the liquid nitrogen. In magnetic, MRI technique is developed initially, but now with the advent of superconductor, very, very small superconducting magnets are there which can go into the detecting all these things. If you have heard some session with regard to Large Hadron Collider, you know that in LHC, Large Hadron Collider, where they are colliding the particles, there the superconducting crystals are being placed, because you know that they are not offering any resistance, so they are being required. So particle colliders are very large, used to accelerate particles. So these superconductors are being tremendously used in the Large Hadron Collider. So I will end up with the saying that the recent discovery of high temperature superconductor big jumps to the giant steps closer to the dream of early scientists. Current application of high temperature superconductors include magnetic shielding device, medical imaging systems, superconducting quantum interference devices, infrared sensors, analog signal processing devices, microwave devices, and communication. So with this, I will end it up, and I hope you are able to understand the concept with regard to the advancing what is happening in the material sciences. And thank you for your cooperation.
Thank you, sir. Any questions from the participants?